Hello, friends. I am Ashish Darbari, founder and CEO of Aximize. To our new listeners, welcome, and to our old ones, welcome back. I have been dreaming for this hour for over a year, and I've been trying to schedule this podcast session with this guest. And thanks to the COVID times that we are in, and people are getting so much busier, it's been a little challenging. But I have a firm authority in formal methods today in-house. And the person I'm talking about is a friend of mine from many years, Professor Supratik Chakraborty from IIT Bombay. Hi, Supratik.
Hi, Ashish. Thanks for having me on this podcast.
No, man, thank you for finding the time. I know things are crazy for everyone these days, and it's been a little
Yeah,
difficult. So, hey, let's start by talking about you a little bit. So, I know you, of course. I think first time we met was about 2005-6 time frame. But, let's share a little bit of your personal journey. I think a lot of people listening in would like to know how did you end up being in science and engineering, and how exactly did you end up being a professor at IIT Bombay?
yeah. So this is like walking down memory lane, and understanding how and why things work the way they do has always been of interest to me. Starting from I don't know what age I was when I opened up a transistor radio that we had at our home, trying to see what happens when I turn this knob and why does the volumes reduce or increase when I turn the volume knob. I don't think I understood fully what was going on, but at least I could see what happens. Some variable capacitor was being tuned as I was turning a knob and all of that. So this interest of how and why things work has stayed on with me, and I guess mathematics and physics really sort of captured my imagination when I was in high school and when I was preparing for college and all of that.
So, hey,
I
Supratik,
mean,
which city did you grow up? Which town in India did you grow up?
I grew up in the town of Kharagpur.
Oh,
It's
right.
a small town in West Bengal.
Yes, yes.
And this is also one of the places where one of the Indian Institutes of Technology is located, although I was not related to the IIT until I joined it for my
Sure,
undergraduate. So I
sure,
was from the town. I was from the town of Kharagpur, which also exists beyond IIT. Okay.
sure.
So, you know, when I went to college, I guess there was this dilemma that, should I take up electrical or should I take up computer science? Because I knew that, or at least I was told that computer science, gives you a lot of opportunity for sort of exploring the mathematical side of things, whereas if you really like physics, perhaps electrical is the right choice for you. And I sort of dilly dallied between the two. And funnily, I sort of got admits in a few colleges in India, and I opted for electrical in some of them, and I opted for computer science in the others. And then finally, when I joined IIT Kharagpur, I had opted for computer science there. So that was my introduction to computer science, and of course, I really enjoyed what I studied at IIT Kharagpur. I mean, it was really an eye-opening experience, understanding the science behind computation, behind computers, and all of that. But then, after my bachelor's, I decided that I also need to learn electrical a bit because physics was a very very close subject to me. And so, for my master's and PhD, I officially enrolled in the electrical engineering program at Stanford.
Right.
I was in the computer systems library, but preparing for the qualifiers over there gave me the opportunity to learn a lot of things about electrical that I had missed out in my undergraduate. And I think it was an amazing experience. I mean, I don't know why there are these boundaries between computer science and electrical. I think
Correct, correct.
these are,
This is, what I find very interesting in your journey is you moved from CS to electrical and you were drawn into electrical because of your interests in physics. And it happened the exact opposite with me. I got enrolled in electrical and electronics engineering, and I got enchanted by computer science. And I want to do a career in computer science. But actually, you're absolutely spot on that these boundaries are absolutely artificial. But when you moved to Stanford and you were doing your master's, you were slowly building up your knowledge base in the things that you were not looking at in IIT Kharagpur. What happened in your PhD then? How did you decide to work on asynchronous designs, and which year was this?
Yeah, so I joined Stanford for my master's program in 1993, and then immediately I took a whole bunch of courses, which are not typically taught in computer science curriculum. So things like digital signal processing, things like device physics
Mm-hmm.
and this kind of stuff.
Yeah.
And for the qualifiers, the PhD qualifiers at Stanford, so we had to choose, I don't remember, some 7 or 8 subjects, and of course there were these subjects also there. So I did study these quite seriously because I had an interest and I also had to get through my qualifiers. But once I was in the PhD program, of course, I had to decide what topic should I focus on, and then I chose something. Actually, my PhD topic was on algorithmic timing analysis of asynchronous circuits.
Mm-hmm.
So I had to understand how asynchronous circuits work, and that was very interesting, very nice. It allowed me to sort of put to use, the different things that I'd learned about devices and about physics of how things work. But at the same time, I guess I could also use my stuff. I mean, it's not only the courses from physics and signal processing oriented that I took at Stanford, I also took core CS courses. And so in my PhD, when I enrolled, I just thought that I should put these two together to see how best I can sort of come up with efficient analysis of circuits which by themselves, I mean, the nice thing about asynchronous circuits is that they are not necessarily as large as synchronous circuits, and clearly synchronous circuits dominate the industry and the design landscape. But analyzing asynchronous circuits is notoriously difficult because you do not get something nice like a clock abstraction that things are happening at clock ticks. So you really have to sort of worry about how signals are interacting with each other at any point of time and what does that do. So, doing something like hazard analysis, figuring out when can glitches appear, when you don't have a clock to stop things from, going at arbitrary times. So this was, this looked very cool for me, and I ended up doing my PhD with David Dill,
I
who,
see.
who had an amazing PhD thesis, and I read his PhD thesis. I mean, he analyzed asynchronous circuits in his PhD thesis using trace theory, and I thought, this is a cool guy to work with because he understands both the electrical side of it and the CS side of it and appreciates it. And of course, I learned a lot working with him. And overall, what I would say is that my journey has been, until I did my PhD, has been trying to learn as much as I could and put to good use all of that learning, both from the CS and the electrical side. And then, of course, when after my PhD, I spent a year as a researcher at Fujitsu Labs of America. And once again, there, I was in the CAD group, which deals with algorithms and also circuit design. And then when I returned back to India, once again, I had to choose between computer science and electrical. And so I said, okay, now maybe I will come back to computer science. It was CS to EE, back to CS. But of course, I keep alive my links with EE folks very much. My first PhD student was co-guided with with a colleague from the electrical department.
Right.
So I had a lot of fun understanding circuits, circuit behavior. For example, this thing about metastability, which
Right.
is when when a flip-flop is trying to latch data and the clock comes too close to the data changing. I mean, this has some really cool physics behind it. And it's very, very interesting trying to understand that and then trying to apply all your algorithmic knowledge to see how best you can avoid this without necessarily uh, cutting down on the performance.
And you mentioned metastability and clocks and asynchronous, and the clock domain crossing is one of the most difficult problems to solve at full chip level. There are lots of vendor solutions these days. They actually have some automated ways of solving this problem, but it has taken everybody a lot of time because it's not just structural, it's also functional. And it's
and I think the phenomenon of metastability is if you look at the physics of what's going on, why is it that something can get hung in a intermediate state, and what are the best ways of coming out about it? I guess people in the asynchronous world have worried about this for a very, very long time, and like brilliant papers written there. Experiments have been designed to study metastability, and it was very, very enjoyable learning all of that and trying to come up with algorithms which help you analyze those things.
So what is interesting is I never knew you enjoyed asynchronous so much, because when I met you, I met you in the context of a completely different topic and field, and I still recall writing you an email when I was traveling to India, and by that time my understanding was you were a formal verification expert researcher. So how did that happen?
So that's very interesting. So as I said, I was a student of David Dill, and Dave was, of course, an authority in formal methods and formal verification.
Of course.
So although I was the only guy in his group who was really doing something related to design and analysis, the rest of the folks in his group were all like deeply steeped in formal methods.
Correct.
So the weekly meetings that I'd have would be much more of a learning experience from me, listening from 10 other colleagues about what papers they're reading and what did they find cool in that paper and what kind of techniques were working out and what were not working. I mean, for example, Murphy, which is from David Dill's group. Some of the people who were developing optimizing Murphy, we were there in the same group meetings every week. We were there a few offices apart, so we would keep talking, chatting. So I guess I was steeped in formal methods while I was there with Dave. Although my PhD topic wasn't really about formal verification, but it was about formal analysis.
Correct.
Where we were trying to design algorithms with proven properties which would help ensure that asynchronous circuits work correctly. So, but over there, I guess I got my hand-holding of what formal methods, formal verification was. And so by the time I finished my PhD, I already knew quite a bit of formal verification, just by being a part of Dave's group. And so then when I returned back to India, I said, well, this is something that I have not, it's so cool, so interesting, but I guess for my PhD, I didn't focus on this, full-fledged, so let me dive into it. And since then, I have been doing that.
Awesome.
But I do keep my links open to the asynchronous world as well, and I no longer serve on the PC of the async conferences, but I did that for a few years even after I came back. But I do keep my eyes and ears open, particularly if something is at the intersection of formal methods and asynchronous. That really gets me excited.
So you're still keeping in touch with your roots. That's interesting. So let me come to this question. So you started a journey in IIT Kharagpur, then moved to Stanford and did CS, then you did electrical, and then came back to CS. So you've been a teacher and a researcher for what now, 2 decades or more?
Yes, 2 decades.
2 decades. So What is your experience of teaching formal methods to graduate students in IIT? I'm certainly interested in the teaching side of this topic.
Yeah, so this is this is something that I have also thought about. That when I teach formal methods to uh, both graduate and undergraduate students here. I mean, we do have a course in our department which is logic in computer science, where some of the fundamentals of formal methods are taught. Um, so most students are swayed by the words machine learning or
Mm-hmm.
artificial intelligence and similar thing, and of course for good reasons. And these
Sure.
are technologies which are really changing the world. Uh, and about a decade back, or maybe 15 years back, networks and things related to the internet and stuff like that were really quote unquote hot. Of course, formal methods is also hot, but in my opinion, but uh, you know, so when students try to take courses, when they enroll for courses, a sort of significant criterion that they have in mind is that how does it tune with job market perceptions,
Mm-hmm.
right? I mean,
Correct.
is the job market really looking for these kinds of areas on your CV, or are they going to, if you say that you have done 3 projects using whatever TensorFlow or PyTorch or whatever, maybe that's better for the job market because there are a lot of jobs out there, presumably, which try to make use of their ML skills. So one of the challenges that we face these days is to sort of get a large number of good students interested in doing things beyond machine learning, and formal methods is one of those things. But interestingly, I mean, this is a very interesting and recent development that even in machine learning, I mean, things have come to a point where you build gigantic, maybe deep neural networks with million parameters and probably billion parameters these days. And then you are talking of using these very complex computational devices in applications where the cost of an error may be very, very high. I mean, for example, I'm sure you're aware of this, that the Federal Aviation Authority, FAA, has been considering this, standard for unmanned aerial vehicles, like drones are going to be moving around dispatching stuff, which is called the ACAS XU. And and this is supposed to avoid collision between these unmanned aerial vehicles. And they are actually recommending using a neural net
Right.
to sort of take the decisions
Mm-hmm.
as these unmanned drones are flying around, and and they have this really long set of rules which are supposed to be followed by things in flight, and the decisions for these are supposed to be taken by a neural net sitting on these drones. And so a question comes that how do you know that this neural net is really doing all that it was supposed to do and nothing more, and not really doing anything which is maybe dangerous. And so this question of formally verifying these machine learning devices is becoming increasingly important. And I guess this is also important when you are sort of using things. I guess there are, you want to use machine learning to sort of identify and classify human beings as whatever, belonging to a certain
Yeah.
category, not belonging to a certain category.
Correct.
Let's not talk about what those categories are.
Correct.
But then you need to offer explanation, and you need to provide some guarantees that some untoward thing doesn't happen. So safety in machine learning, I guess, is becoming very important. And so therefore, it's again formal methods to the rescue there. I mean, there is really no other way to.
So are
sort of
your
prove that.
students, so sorry to interrupt you, are your students buying into this? Are they feeling excited that you're actually talking about, in my opinion, two very hot topics, machine learning as well as formal? What?
Yeah, so I have actually offered a course in the current semester, which is about formal methods in machine learning.
Awesome.
Okay. And yeah, I had, in the first few classes, there were actually quite a few students. I mean, I didn't expect that many. But then I also set the rules of the class and said that, well, you've got to do a project, you have to show me that this thing works, it's not just reading papers. So, of course, some people dropped out thinking that the load might be heavy or whatever, because it requires them to read papers, roughly 2 papers a week, understand those and solve some problems related to those, and then also pick up a project where they can apply a tool, a real tool that has been developed as part of these papers, and then sort of see the strengths and weaknesses. But what I'm trying to say is that with this, newfelt need, I guess, or newfelt urgency of safety in machine learning, this is, I think, yet another area where I think formal methods has a big role to play. A real big role.
I think formal has a role in everything. I recall a chat with Harry Foster many years ago, and we were
Mm-hmm.
sitting in a social environment, and Harry was pulling my leg, and he was asking me, saying, "So tell me, Ashish, what can formal not do?" And
Mm-hmm.
I used to say, well, the only thing you can't do with formal is make love with your wife. But other than that, other than that, you can use formal for everything. I think it's not so much the fact that we have to use everything deeply formal, mathematical to the last T, although that would be ideal. But I think it's the process of reasoning and
Yeah,
thinking about things in a structured, logical way, which is what I
yeah,
think you are trying to teach students. And I think
absolutely.
this is a great, this is really a great opportunity. So, are these courses available for anyone outside IIT or?
Yeah, so I guess from my course webpage, from my homepage, there's a
Mhm.
link to my course webpage, and from my course webpage, I at least put up most of the material, and I also try to put up some of the explanatory. I mean, now that things are online, I have prepared some explanatory videos on my own.
Excellent.
I mean,
Okay.
not about everything, but about some of the stuff, and I have put them up there, and then. So the real interaction with students happens through, in our case, Microsoft Teams,
Mhm.
where it's a separate channel for IIT's
Sure.
students and faculty.
Sure.
So those things, I guess, are not publicly available,
Sure.
but there are some parts of it which are publicly
Awesome.
available.
That's very useful to know because we launched this new course and you kindly reviewed it. And now, what I'm going to do just after we jump out of this chat is going to give a reference to students so they can come and look you up and find more
Oh, great.
interesting reading material.
Yeah, yeah,
So this would be great.
yeah.
Hey, so I'm trying to talk to you, about what? Symbolic simulation. So
Yeah.
so you and I worked on this initially, and you said, oh, you liked STE, and then we worked on a project back in the days when I used to be at Southampton. But you took it really seriously, and after I moved on to industry,
Mhm.
you kept working on this and developing word level STE solutions, I believe, together with Carl Seeger.
Yes,
So
yes,
tell us a
yes.
little bit about that, man. Where are we with word level STE? And
Yeah, yeah, that's another very interesting line that I'm still sort of working somewhat you know on in the sort of
one of the many projects.
yeah, in the sense that I mean there are other things that have come to occupy my time, but I still go back to this thing. So I mean I guess this is no secret that when you want to do reasoning about data paths, right? And if you do bit level reasoning about data paths, then as your data paths become wider, then it's difficult to scale up that reasoning, right? You go from 64 to 128 bits, and uh, the complexity of reasoning at the level of bits has gone up from 2 raised to 64 to 2 raised to 128, and
Correct.
that's not pleasant. Okay. So, but I mean, you're probably still doing addition of words. I mean, earlier you were adding 64-bit words or multiplying 64-bit words. Now you're adding or multiplying 128-bit words. So if we can lift the reasoning from bit level to word level, then perhaps a lot of the reasoning that I did for 64-bit words will just be usable again at 128-bit words, or whatever. Maybe if you go even beyond that. So the idea of doing word level reasoning, the idea of sort of formulating verification conditions at the word level has this huge appeal. It has this huge promise that if you can really do the reasoning at the word level, if you don't need to blast it into bits, then it just scales up so much better, and it's kind of oblivious of what was the word width. You can sort of apply the same reasoning. Right?
So let me stop you here. So I have been badgering all of the EDA vendors, and even when I used to be at OneSpin, had numerous talks with their R&D teams to build word level solvers, and everybody tells me building word level solvers is a great idea, but very hard to implement.
Yeah, so I think that's true, but I think there is a lot of very, very interesting stuff that has happened in the world of SMT solving, satisfiability modeling theories. And I mean, there is an SMT competition that is held every year. And if you look at the trend of how SMT solvers are developing, in the sense of what the complexity of problems they can deal with and their performance, the speed at which they can solve it, I mean, it's just really growing quite fast. In fact, it appears that SAT solvers, of course, you can solve a problem in the theory of bit vectors by blasting it out and throwing the latest and coolest SAT solver on it. But really, for a very large class of problems where the reasoning is really at the word level, I mean, bit level, word level solvers, bit vector solvers can really beat the hell out of SAT solvers. And they can scale up so much better. And in fact, this is one of the main reasons why we went into word level STE, because we felt that SMT solving technology, I mean, this was around, I guess, several years back.
Correct.
7 years back.
Correct.
We felt that SMT solving technology for bit vectors was already at a stage where if I could formulate the problem in terms of words parameterized by certain widths and just throw it in a SMT solver, I would probably get better performance than just solving it at the bit level and throwing it at a SAT solver. So, this was kind of vindicated by Carl. So I did this work with two very amazing colleagues from who were then at Intel. And Carl was at Intel Strategic CAD Labs at Oregon. And of course, now he's moved out of Intel. He's at Chalmers University. And there was another colleague from Intel IDC at Haifa in Israel, and Zurab Khashidashvili. And basically, we decided to, sort of give this a very serious shot. That why not formulate STE as word level constraints and then piggyback on the power of SMT solvers, which is only going to improve by the day, to solve problems at the level of words.
Correct.
And I mean, this idea sounded really cool. But the primary problem with this, I mean, you've worked with STE a lot, so you know this, that when we implement STE, I mean, the theory is nice, but when we implement STE, we use dual rail encoding.
Correct.
Right? Because we have to use 0, 1 and sort of X.
Yeah.
Now, what does it mean to say X for a word, right? Suppose, I mean, for a bit, I can say, yes, it is 0, 1 and X. Now, if I take a 64-bit word, I don't want to say all the 2 raised to 64 values that the 64-bit word could have taken or X, because that becomes a very large set to deal with.
So I'll tell you one thing we do in hardware verification SVA style, and the system Verilog semantics for $ is unknown, is that if any of the bits in the word is unknown, then we would classify the whole word as unknown.
Exactly.
So that is a very strong abstraction, and probably.
No, but that I think is a very useful abstraction, because what happens is you do not want to treat individual bits as unknown, because how does it matter if in a 64-bit word bit 3 is X or bit 27 is X, or both bits 3 and 27 are X. So that, of course, is the first thing that comes to mind. But then when you also look at designs that use words to sort of do computation, you also see that there are these operations which sort of take a slice of a word, and maybe they take a slice from, so maybe there's a 64-bit word, but the first 32 bits are always together. The second 32 bits are sometimes used
slicing,
in some ways, right? So the idea was here to say that, okay, let's take a word level design and let's find out what are the divisions of those words which are never treated
differently. Correct.
Right?
Correct.
So we want to find out these atomic parts of the word which are always treated as a unit.
The famous ip and dill paper on scalar sets, right?
Yeah. Right. So and then we want, for each of those, we want to treat it as either a word or just X, without worrying about which bits are X. So this was the next logical step. Now the third step after that, which actually turned out to be quite difficult, and I think that was kind of the major contribution of the work that we did, was to say that now we have to define this algebra. I mean, if I'm saying A plus B, so I have to say what does it mean to talk about A plus B, where A is a 64-bit word, maybe divided into two 32-bit chunks, and one of those 32 bits can take on the value X. And I have to do all of this in a symbolic way, because it's not simulation that I can look up the value and say what it is.
Correct.
So we actually came up with this technique where we said that if that word level atom that you're dealing with is, let us say, k bits, we're going to use k plus 1 bits for it. And that extra bit, we will design a logic which will tell us when that extra bit is set or unset. And if that extra bit is set, it means the values of the remaining k bits are to be ignored. And essentially now we started talking about words with an extra, just like words in a cache have a dirty bit.
I was just going to say that. It's just pretty much the same idea.
It's pretty much the same thing. But now we have to design a logic saying that, what if I'm trying to add two words where each word is maybe divided into 2 or 3 parts, and the dirty bit or the invalid bit, as we called it, for each of those subwords are some symbolic expressions, because they are themselves dependent on other things that have happened in the past. And so we had to basically build up this logic of invalid bits, saying that given invalid bits of operands and values of operands, how do we figure out the invalid bits?
And all of this work is being done in the verification model, not in the design model. So you're reading, parsing the design model, and then annotating the design model, basically extending the design model in the verification domain. It makes a lot of sense. Yeah.
And then we had to prove that whatever logic we have designed for these invalid bits really captures all possible cases.
Yeah, that is a tricky bit, right?
Yeah. So so we had to finally prove a theorem that anytime you're giving arguments with given invalid bits, which would not uniquely determine the value of one of those subwords, the invalid bit of that subword would get set to 1. The logic has to ensure that, because otherwise we don't have completeness.
Right.
So that was the hard part, and I guess we finally came up with that logic for a whole bunch of RTL operators, including things like division and shifting, and memory accesses, and this and that. And then we finally put all of this into a tool, and we let it run on. We started off with some toy benchmarks, and then I had a student who actually did an internship at Intel and actually ran it on Intel's designs, and it did show a lot of promise. And then Carl and Zurab, my collaborators from Intel, said, okay, let's put this in the, I guess Intel has a whole bunch of tools that they run in parallel. And they said, okay, this is going to be one of the tools that they're also going to run in parallel. And it went up to that stage, and I was getting some good feedback from my collaborators there. But after that, I guess Intel went through a massive reorg,
Mm-hmm.
and Carl left Intel. Zurab moved out of the verification group, and he's doing machine learning
Wow. Okay.
in Intel. And so I believe it's out there,
Yeah.
because I mean, Carl keeps telling me that he's really, I mean, he thinks that this really solved one of the problems that they had, extending ST to words. And of course, Carl now at Chalmers University, he's on this massive project where he's rebuilding Forte
Right.
for
That would be
an
awesome.
academic, open
That would be
source
awesome.
version. And this, he says, is going to be part of that, whenever the new incarnation of Forte is going to
Awesome.
come out.
Awesome.
So that was a very, very, multi-year project with some of, and Carl is of course an authority in ST.
He's an
the one who
authority on
started
many.
this
He's
whole-
an authority of many topics.
Yeah. And it was really amazing to work with him. I mean, he could, sort of see ahead about
Right.
what things would work,
Yeah.
what things wouldn't.
Yeah. Okay, friends. So we've got to resume this chat next week. I know you guys want to get more out of it, and so do I. So we will continue talking to Professor Supratik Chakraborty, and we'll continue having these detailed deep dives into many technical topics. So do join us next week. Till then, keep safe, keep healthy, and we will be back soon. Thank you very much.